All right, this is section 5.2, part 2. Now let's look at local behavior of polynomial functions. Okay, so a turning point of a graph is a point in which the graph changes direction from increasing to decreasing or from decreasing to increasing. So notice right here we are increasing, and then we hit this little point right here. We call it the turning point because it changes from increasing, and now when we get over that point, we are now decreasing. Now here we are decreasing, we get to this point right here, and then we change from decreasing again to increasing. So that's what we call a turning point. Now when the graph crosses the the y-axis, that is called the y-intercept. And when we know when the graph crosses the the y-axis, we know that x is equal to 0 at that point. And when the graph crosses the x-axis, as it does here, here, and here, we know that the y value is equal to 0 at all three of those points right there. Okay, so those would be x-intercepts when you cross the x-axis, and a y-intercept right there. It's really close to that turning point when you cross the y-axis. Okay, now a turning point, we said it changes the directions from increasing to decreasing or from decreasing to increasing. We already looked at the y and the x-intercepts. Now here's the important part here. A polynomial of degree n will have at most n, the same as the number of degrees, x-intercepts, and n minus 1 turning points. Okay, and we also called x-intercepts real zeros or roots. So x-intercepts, we can say those are also called real zeros, or we can say those are roots. So you can say there's n real zeros, there's n roots. So the same number as the degree. So let's look at this. Consider the function f of x is equal to 6x cubed minus x raised to 12 plus 7 x raised to 8 minus 2. Now the degree of this function is the x raised to the highest number, so that would be 12. Okay, so we're going to have 12 x-intercepts and n minus 1, so 12 minus 1, 11 turn-in points. Okay, same thing here. Here's our function. It looks like the degree is 5. So the function will have at most 5 x-intercepts and 4 turning points. Okay, what is the least possible degree of the polynomial graph below? How many turning points are there? How many x-intercepts are there? We'll go ahead and look at the x-intercept. So that's where the graph crosses the x-axis, and it looks like it crosses it here and here. Okay, so that would be 2. Okay, now, so when you got, for this case, 2 x-intercepts, that means that the degree of this polynomial is at least 2 or greater. Now let's count the number of turning points. Okay, so we've got 1 turning point here, 1 turning point here, and 1 turning point here. So I have 3 turning points. Okay, so we know that turning points is n minus 1. That's equal to 3. Well, n's the degree of the polynomial. So if I solve for n, the degree of the polynomial should be 4. So what I do is I count the number of turning points that I have, and then I just add 1 more, and that's going to give me the degree of the polynomial. Okay, so that's the least possible degree. So it could be 4 or it could be bigger, but we know that that is the smallest possible number for the degree of this polynomial. Okay, so let's look at the x-intercept. So we've got 1, 2, 3, and then I have 1 turning point, 2 turning points. Okay, so that means I add 1 more to the turning point. So the least possible degree for the polynomial would be 3. Okay, let's look at this one. Okay, so x-intercepts, so it looks like I have 1, 2, 3, 4, 5 x-intercepts. Let me get rid of those. And then I have 1, 2, 3, 4 turning points. And then what's the least possible degree of the polynomial? We'll add one more to the turning points, and that would be 5.